Welcome back, ladies and gentlemen. Today, we've got a good one. We're going to be talking about shift registers. And so, what's a shift register? Well, lots of times we need to save a value. If this were a programming language, we would just create a variable. If it was C, we could do something like, say, int x. I want an integer called x. In hardware, though, our lives are always harder. Remember that we have to actually create in hardware a place to save a value. We call these places registers. And so if I wanted to save 1 byte's worth of information, I would create a register 1, 2, 3, 4, 5, 6, 7, 8. So notice that in this we could save exactly 8 bits. 4, 5, 6, 7. Yep, got it right. So we could save 8 bits there. Remember we learned in our latch lecture that this could be simply 8 D latches in parallel, or 8 D flip-flops in parallel. And honestly, that would work fine. We could basically, remember we would put them all in parallel, and I could save everything in here all at once, and we would have our value. Turns out, though, that sometimes we can give these latches, we can give these registers just a little bit more functionality, and it makes them way more valuable. Let me give you an example. Let's say that I have a program that needs to multiply or divide by 2. I want to build a circuit that has to multiply or divide by 2. Remember, this is something that happens quite often, especially because everything in a digital system is based on powers of 2. So if I had a number, let's use the number 10. Right, so number 10, 1010. And let's say that I wanted to multiply everything by 2. I want you to notice something. If I shift this number left by 1 bit, and what I mean by that is I take 1, 0, 1, 0, and I add a 0 here. So notice everything I had before moved over to the left by 1 bit, and I put a 0 here. Notice something. What's this number? Well, this is 1, 2, 4, 8, 16. So this is the number 16 plus 4, which is 20. Notice that by shifting left, I multiplied by exactly 2. Let's try shifting to the right. If I had 1, 0, 1, 0, and I shift it 1 to the right, that's going to leave me with 0, 1, 0, 1, or the number 5. And so this is just a really simple example to show you that if I want to multiply by 2, I can just take a value and shift it to the left by 1. If I want to divide by 2, I can take a value and shift it to the right by 2. And so there are many other uses for shift registers, and today we're going to learn about more of them. So this page here sort of gives you all the different ways that they can come. Notice this would be what we call a serial in, meaning that the values have to come in one at a time. We shift right and serial out. So this is serial in, shift right, serial out. Same sort of thing going on with this guy. It's just serial in, shift left, serial out. This one here is a parallel in, serial out. And so notice, remember we talked about this before, that lots of different parts of computers are in parallel, like our data bus inside the computer, where all data flows, that's parallel. But remember, things like USB are serial. And so we need some way to convert from parallel to serial. We can use this guy for that. The data bus can drop its values in parallel, and then this register can shift them out in serial one at a time to our USB bus. Over here, we have serial in, parallel out, and then here we have the one that's most commonly thought of as memory. Right? This is like a normal value that we want to save in a register. So we save it in parallel, and then we grab the whole thing out in parallel. Finally, we have these two weird looking ones over here, which are called loop registers or ring registers, and we will talk about them near the end of today's lecture. So again, serial in, shift right, serial out, serial in, shift left, serial out, parallel in, serial out, serial in, parallel out. Parallel in and out. And then finally we have rotate right and rotate left. Because again, notice that everything moves to the right and whatever was normally going to be kicked out is rotated all the way back over. And then again, we have rotate everything to the left and move what was over at the end all the way back to the input. Alright, so let's look at how one of these could be built. And so remember from last lecture, a D flip-flop is simply a flip-flop where whatever we want to save, we put that on our input. And then whenever the clock goes high in this case, because notice it's a positive edge triggered, it'll save the value. And so to create a serial in, shift right, serial out register, it's really simple. I just put them in serial, one after another. And so now notice that we have a 1 on this first input. What's going to happen when the clock strikes? Well, if you said that this flip-flop is going to save a 1, you'd be absolutely right. So, clock strikes and boom, that 1 gets saved here. But now notice that this one's input is coming from the output of this one. And so on the next clock strike, what's going to happen? Well, that 1 is going to get saved into the next one, and then into the next one, and then into the next one, and so on. And so you can see it's really easy to build a shift right register. Serial in, shift right, register. Okay. Again, we could do this is showing you one of our applications of a serial to parallel. So again, we talked about this before. Remember that USB stands for Universal Serial Bus, but when we want to save the values that come in from USB to the computer, remember that the internal bus on the computer is all in parallel. So this shows you one way we could do that. I pipe in everything I want in serial, just like we did before. So notice in this case, we're saving the number, we've got 8 plus 4 plus 1. So that's going to be 13. I want to save the number 13. And then, boom, that number is available after 4 clock pulses in parallel to whoever needs it. Alright, so we're looking a little bit more complicated here. This is another way that we could build this. This is a real chip using SR flip-flops. What I want you to notice is that it's not quite as complicated as it seems. So notice that, remember we talked about this in the flip-flop lecture, that we have both synchronous and asynchronous inputs on our flip-flops. And so that's what this clear is. Notice that we have a negative inverted clear here at the top. What I want you to be able to do in your mind is notice that we've got a bubble here and a bubble here. Those two bubbles will cancel each other out. And so notice this bubble here cancels essentially all of these out. You can kind of think of that in your mind. Because it's just like if I had an inverter going directly to an inverter. Those two cancel each other out. If I have a 1 at the input here, I'm going to get a 1 at the output here. Because this 1, as it gets inverted, turns to a 0, but then turns back to a 1 when it gets inverted. And so whenever we have two bubbles that are directly in a row, they cancel. And so notice, if I have, this is a inverted input, so I should put 0 to clear it. So if I put a 0 here, because I've inverted those two, I'll get a 1 here, and the 1's going to cause each of these to clear. So that's what that first one does. I'm going to erase this just so we don't get confused going on with all the writing on here. Alright, next up, we've got our clock. Our clock is right here, and again, notice that, again, we have an inverter, but it's inverted with each of our inputs. So that's not going to bug us. This will still be a rising edge flip-flop. Or actually, I should say, this must have been a negative edge flip-flop, and by putting the inverter here, we make it rising edge at the output. Alright, now, let's look at these two things. So we have a serial A and a serial B. And what that really means is that one of these is going to serve as an enable for us. So again, notice that we have, let's just take a slice of this. Let's just look at this one right here. And so what I have here is I have an RS flip-flop, RS, and this one is inverted, and this one is not. But notice that we have this here coming from a NAND gate. And so it's kind of like having an inverter here. And so what I want you to see is this here actually works a lot like a D flip-flop. Because if I have a 0 here, that gets inverted here. And we have our 0 coming on the 1 on S, but that gets inverted and goes into the S like a 0. And so notice, with an RS flip-flop, or actually I should write it the way we normally do, with an SR flip-flop, if I have a 0 on S and a 1 on R, that saves a 0. So notice with a 0, I save a 0 into this thing. If instead I have a 1, well, this inverter is going to invert that and give me a 0 on R. It gives me a 0 here, but again, remember, this inverter turns that into a 1. And so on my SR, when I have, remember, a 1 under S and a 0 under R, that saves a 1. So what you really see here is each of these flip-flops here is essentially being used like a D flip-flop. That's why they have, again, the inverter at the output going into R and going into S. It goes directly into S. And so, now why do we have this AND gate? Notice that, remember, we talked about this before. If I have an AND gate, and I want a signal to pass, but I want to be able to stop it from passing, I can use that second input. We'll call this, actually, instead of S, so I don't confuse people with set, let's call it A. If I put a 0 here, and a 0 here, I get a 0 at the output. And so by putting a B on 0, I've ensured that there's a 0 at the output. If I put a 1 on A, and I leave B at 0, then I still get 0 at the output. And so notice that we can kind of use this like an enable. If instead on B, I put a 1, then if I put a 0 on A, I get 0 at the output. But if I put a 1 on A, I get 1 at the output. And so again, this allows us to use one of these two inputs as an enable that stops other values from getting through. And so notice this is that same thing we just looked like, but it's how it's really built inside the computer. So we saw the one with a bunch of D flip-flops, but remember, at the end of the day, D flip-flops are built with RS flip-flops, SR flip-flops. And so again, this is the same device we just looked at. It's just it shows the ability to asynchronously clear everything, and it shows us how to actually build it using SR flip-flops. Alright, so this is the type of example that I sometimes give on exams, and I want you to be able to figure out. Let's see what this one can do. Well, notice that we've got our simple version here, so we've just got 4 D flip-flops. And this one supports 2 modes. It supports something called shift and something called load. So first up, let's see how this works if my shift load line, is set to 0. Well, if I have a 0 coming in here, right, that means that notice we have a 0 on this line, a 0 here, a 0 here, and a 0 here. A 0 going into an AND gate, remember, is going to kill that AND gate. So none of these, all these are going to pass nothing but zeros. And so it's essentially killed them all. If we look up here, there's an inverter. So on these lines, we have all 1s. And so notice that 1 is essentially enabling this AND gate. And so whatever we have on this side of the AND gate, we get here. So D0 passes here. Notice whatever we have on this side, D1, because this is enabled, we have a D1 here. So we have a D2 here, we have a D2 here. We have a D3 here, we have a D3 here. Now we've got our OR gates. Remember, if we've got one side of an OR is 0, then whatever's on the other side is what passes. And so we have D1 here, we have D2 here, and we have D3 here. And so notice what we just did is when the shift load line is set to 0, we are saving whatever is in parallel onto our flip-flops. That's why it says it's a negative active load. And so we're loading this in parallel whenever we have it saved to 0. Alright, let me erase all our marks here. And now what we want to do is let's see what happens when our shift load line is set to a 1. Well, if this is set to a 1, that means it activates this AND gate, it activates this AND gate, it activates this AND gate. And notice, because it's a 1 here, this turns this to a 0, this to a 0, this to a 0, and this to a 0. It thereby kills this, forces a 0 here. It kills this AND gate and forces a 0 here. It kills this AND gate and forces a 0 here. And finally, it kills this AND gate and forces a 0 here. Now, notice that starting from the left, this AND gate will always store a 0 when that shift line is set to 1. Notice that this AND gate here gets its input from here. Notice that again, this side is dead. It's always going to give a 0. This side, however, is active. So the input's going to come from this side. And this comes from Q0. So now, whatever comes on the clock strike to D1 will come from Q0. Again, notice that this output here comes up. This AND gate is active. So it comes to our OR gate and gets saved in here. Same thing with this one. Comes up from here, goes to our AND gate, which is active, and gets saved in here. So notice that this here is actually a shift right register. So it is a parallel load, shift right, serial out. So parallel in, serial out, shift register. Okay, so what we have here is the 74HC165, which is an actual CMOS shift register that you can buy. Notice that what this one has a few options. You can do the shift. We can see from the SRG that it's a shift right. So by putting a 1 here, we can shift right. We can put a 0 here and do a parallel load. Notice that unlike the previous one, it gives us a serial input. And so I could just use this without the parallel at all and just do a serial input and then shift it over and then serial output it as well. One of the other things this has, I think this is the first time we've seen it, it's got our clock input, but it also has a clock inhibit. So what that allows us to do is it's kind of like an enable on the clock. And I like these things because it means that we can inhibit the clock, stop the clock from making it in. The way that it really works is that inside this chip there's an OR gate. And you've got the clock coming in on one input, and you've got this clock inhibit on the other. And what happens is notice that this is it's not inverted, there's no bar over it. And so if I stick a 1 on this clock inhibit, no matter what this clock line is coming in, this is going to be pinned at a 1, right? Pinned at 5 volts. And that means it's not getting its low to high rise every time the clock strikes, and so the clock doesn't work. The shift register doesn't shift. If instead I put this to a 0, then our clock signal is going to pass through like normal. And so that's what clock inhibit does, and this is the CET1110C. Yeah, they're saying what I just said. Okay, so we again got another setup here. Let's see how this works. Notice we've got a bunch of D flip-flops, and they're connected to a whole bunch of garbage at their input, but there's really only a few places we can play around with. We have our clock. That's just going to do what clocks always do. It's going to go from a 0 to a 1. Notice that we've got a serial data in, so we'll look at that in a minute, but there are really only one configuration line that we can mess with. This right, left, whatever that does. So let's start there. Let's say I put a 1 on this line. Well, if I put a 1 on this line, first thing I notice that's going to do is it's going to stick a 0 here. This 0, remember, is going to kill this AND gate. Because no matter what comes in here, we're always going to get a 0 at the output. And if this is an OR gate, it's essentially just going to ignore that line. All it's going to matter is what comes in on this side. So that 0 is going to kill that one. This 0 will kill this one. A 0 here will kill this one. And finally, a 0 here will kill this one. Okay, that 1, however, will activate this one. So this one's activated, this one is activated, this one is activated, and this one is activated because they're all getting 1s. And so now what I want to do is I want to see, this is over here, where is this one, this D flip-flop getting its input now? Well, the input comes this way, and notice that because this side is in effect dead, all that matters for the input is what comes here. This AND gate is active, and it gets its input from the output of the one before it. This one here gets its input, again, from the one before it. This one gets its input from the one before it. And finally, this one here gets its input from that serial in. So notice what this is doing. This is doing serial in, shift, right, when that right-left line is set to 1. And that makes sense, because notice it says an active high gives it a right. Alright, now let's erase all this and see what happens when we do it the other way. Okay. Now, if we give it a 0 on this line, that 0 is going to kill this AND gate. That 0 is going to kill this AND gate. It's going to kill this AND gate. And that 0 is going to kill this AND gate. It's going to activate because we have a 1 here. This one, this one, this one, and this one. And so now, let's see where each of these gets its input. We can see this one here gets its input because the one activates this AND gate. It's going to get its input from, it looks like the serial in. This one here is going to get its input. And if we come this way, it's coming over this way. And so it's getting its input from the one over. So notice that the one here is shifting its input that way. This one here is getting its input. If I follow this here, it's kind of confusing, kind of hard to see. Kind of see it coming there. So it's getting its input from the output of this one. So this one is shifting its value this way. This one here is getting its input, again, across, over, and from the output of that one. So it's shifting its value this way. So notice this is doing serial in, shift left. And notice we can see at the bottom here, we have parallel out as an option from all 4 of these lines. Notice that the output here is connected. And so this allows us to do serial in, shift right, parallel out, or serial in, shift left, parallel out, all based on what we put on that right left line. Not too shabby. Moving on. So we talked about those 2 things at the end, the ring counters. We can build these with D flip-flops or JK flip-flops. We're just going to look at the D. They both work the same way. And so notice the difference is here. We don't have a serial in. Instead, we start something here. Let's say that this first one is a 1. We've got a 0 saved here, a 0 saved here, and a 0. Let me go back. And a 0 saved here. Notice that when the clock strikes, this input is going to move over here. This input is going to move over here. This input is going to move over here. And this one is going to be carried all the way back. And so it allows us to rotate through a set value. Now these have a lot of uses. One of them is, imagine if we had 4 7 segments here. 4 7 segment displays. And I only had 1 decoder. What I could do is I could activate only one of these at a time, and we could display the number. And then we could, over here, first go through 7, then say we want to show 3, basically switch through these 4 fast enough to the decoder, and using this ring counter, only activate one of these at a time, so we could show a number that looks like it's on all 4 of them at once, when really we only have one of them powered at a time. We just gotta switch through them so fast your eyes can't see. This is a really common way to drive 7-segment displays. Things like our multimeter on our desk. All of those lights are probably not on at the same time. They have a system like this set up where they're switching through them so fast that you just can't see it. That saves power, it saves components, all sorts of things. And so again, this is a ring counter. Reason it's shown like a ring counter is you notice if I draw it out this way, we can see that it looks like a ring. And notice it's the same thing. This is where the output of F0 goes to the input of F1, the output of F1 goes to the input of F2, F2 goes to F3, and then F3 goes back to F0. So that's why it's called a ring counter. If we were to look at one that had 8 bits, you can see, and I put a 1 on only one of them, so we had a 1 with all 8 zeros, or all 7 other zeros. We can see that it would look like this on the waveform, right? It would start at Q0. When the clock striked, it would go to Q1, then it would go to Q2, then it would go to 3, 4, 5, 6, and 7. And again, we could use this to multiplex something like those 7 segments we saw. So there's actually an additional type. We just looked at the ring counter. The problem with the ring counter is it has limited states, meaning if I have 4 of them, I can only have 4 different states, right? Like if we have 1, 0, 0, 0, I can have that, I could have this, I could have this, or I could have this. And then as soon as the clock strikes again, we go back to this one. Sometimes we want to have just different states. And to do that, we can use what's called a Johnson counter. It's also called a flipped ring counter sometimes. And so notice that a Johnson counter looks almost the same as the ring counter. The only difference is instead of getting the input from here to go back, which is what we would do in the ring counter, we instead take it from the invert. And what this does is it allows us to essentially double the number of unique states that we have. We'll see that in just a second. So now notice it's also called a twisted ring or a twisted pair counter, because instead of being like the ring counter where we go straight in, basically we take the invert and use that to drive the input. And so here, right, notice that after the first clock strike, this gets brought back, but it gets inverted. Then we shift everything to the right again, this gets brought back, but it gets inverted. This gets brought back, but it gets inverted. And so if we were to continue this pattern, what would be the three remaining states? Pause here and see if you can figure it out. Okay, so the next state, right, this would get brought back, but it would get inverted, and so we would have 0, 1, 1, 1 for state 5. Next we would have 0, 0, 1, 1 for state 6. Then we would have 0, 0, 0, 1 for state 7. And then finally notice after state 7 we would go back to state 0. So as before, remember with a ring counter and 4 bits, we could only have 4 states. With a Johnson or a twisted pair counter, notice we can, with 4 bits, get 8 unique states. And sometimes that's useful. One of the other reasons we can use shift registers is to delay signals. Sometimes you may have different parts of a circuit that are calculating some sort of result or sending a message, and we need them both to arrive on time, but maybe one completes sooner. We can use this shift register. So notice this is a shift right 8, so it's got 8 bits and it shifts to the right with a serial in. So serial in, right 8. And notice that every time something comes in at the input here, it has to flip 8 times before it makes it to the output. And so if I want to delay a signal by a predetermined amount, I can simply use a shift register. Because notice, to get from this side over here, the left side, to the right side, it will take time. Remember that if I want to know how long cycle time is, it's 1 over frequency. So 1 divided by 40 times 10 to the 6th. Right, so we got 40 megahertz, so that's 10 to the 6th. Times, in this case, 8 clock cycles before it makes it out. And that'll tell us how long it takes to get to the right side. So we can see we have 1 divided by 40 microseconds is 25 nanoseconds. Since it takes 8 of them, this is going to delay this signal 200 nanoseconds before it makes it to the output. And then again, this is sort of the example I gave you before. Remember that the data bus inside of the computer is in parallel, but a lot of devices like USB are serial. So we need some way to go from parallel to serial. And so notice, all the data bus has to do is it basically takes that information, stores it in a buffer. When it's ready to send data out, it'll send it into a parallel data register for sending it out. It can then put that into a parallel to serial shift register like we saw and clock those bits out one at a time in serial. Likewise, when we have serial data coming in, we can use a serial to parallel shift register, clock it in, and then take that parallel data and put it back on the data bus. So finally, we're at the end of the lecture. Remember that a register is one or more flip-flops used to store and shift data. One storage element in the register is the stage. So like when we shift right, we're shifting it right by one stage. Shifting is to move left or right. We can load in parallel to bring the data in parallel. And bidirectional just means it can shift in 2 directions, either left or right. So let's see if we can answer these. The shift register that would be used to delay serial data by 4 clock periods. So I want to delay my serial data by 4 clock periods. Which one would I use? Well, we would want to do this. We know it's this one because it says we want to delay serial data, so it shouldn't be any of the ones that allow parallel in. And again, we just want to delay it. We don't want to get parallel out. And so remember, this will delay it by 4 clock cycles. Next up, can you get this one? Take a minute. Okay, I'm going to give you the answer, so pause it if you haven't got it. Which one's this one going to do? Well, we can see we've got something that says shift load, so we can kind of assume it's going to do a parallel load, right? But we still got to figure out which way it shifts. I guess we don't for this problem, but you should, right? If this is a 1, right, that means it's going to kill anything that's attached to here, so it kills all of our parallel lines. And let's see where the serial lines come in from. So we've got this that comes from the one before it, this comes from the one before it, this comes from the one before it, and this comes from D0. So this looks like to me, it could be parallel in, shift, parallel in, serial out, shift register. And more specifically, we know that it is a shift right. If the shift load line is high, what happens to data? Oh, I think this is the one I just did, right? And yeah, I solved the next one for you already, but it's going to shift it right. And we saw that because that means it comes from here. A 4-bit parallel in, parallel out shift register will store data for how many clock periods? What do you think? So the answer is going to be 1 clock period. Because remember, if it's in parallel, they all come in at the same time, and they all leave after 1 clock strike. So this device has 2 serial inputs. If data is placed on the A input, the B input could serve as an active low enable, could serve as an active high enable, should be connected to ground, should be left open. Well, remember we talked about this structure before. Notice that if I take this bubble and that cancels that out, that would mean that I have an SR where we have a bubble before the R and we have the S coming in directly. If this is a regular AND gate, if I have a 1 here, that's going to cause our set line to be high and our R to be low, so that'll save a 1. If I have a 0, that's going to cause the R to be high and the S to be low, and so that'll save a 0. So notice with the AND gate, if I get a 1 at the output, it's going to save a 1. If I get a 0 at the output, it's going to save a 0. And so that means if I want the data that's coming in on A to be saved directly just as it is, we need to tie B to a high. And so what that tells me is B could serve as an active high enable, meaning when B is set to high, everything that's coming in gets saved exactly how it is. Notice though, this is kind of a weird circuit because if it's set to 0, it's still going to save 0. And so that's not really a great enable. I like the one on the clock inhibit better. What could be a possible sequence for a 4-bit ring counter? A, B, C, or D? Try this one. Pause it for a second, make sure you can get it. Okay, so remember, if this is a ring counter, that means it cannot be this one. Well, it couldn't be this one anyway. This one couldn't be a ring or twisted because notice that this to this is okay, because that could be twisted, but then it couldn't go to this, because again, this got taken over directly. So this next one, we've got the same problem, right? It could be a twisted one from here to here, because this 0 gets brought over and gets inverted, and that gives us this. But then that would mean this one has to get brought over and also get inverted, and it doesn't. So that one can't work. This can't be either ring or twisted. Notice this one here comes over, and it gives us this, so it's inverted. Next up we have this one come over and get inverted. So this one here could be the Johnson. And then here we have this one get moved to the right to do this. So this gets brought over and it gets moved over. Then this gets brought over and it gets moved over. And so this is the only one that can be the ring counter. So this one could be a Johnson counter, but not a ring counter, and these two aren't either. Alright, what's this circuit do? If you said Johnson counter, you got it. Because notice that, again, it's a ring counter. Not a ring counter, it's a rotate device of some sort, because each one is being fed by the input of the previous. But notice the last one, it comes from the inverted line, is what gets saved. And so this is our Johnson counter. Assume a serial data is applied to the 8-bit shift register shown. Clock frequency is 20 megahertz. How long will it take for the first data bit to show up at the output? Go ahead and try this. Okay, so again, remember, this tells us it's going to shift right in serial 8 times. And so the first thing I need to figure out is how long is one clock cycle? Well, time is equal to 1 over frequency, and so each clock cycle is going to be 1 over 20 e to the 6, 20 megahertz. And so to get this answer, we simply need to know that the total delay is going to be equal to 1 over 20 e to the 6 multiplied by 8, because it takes 8 cycles. And so if you do that, you should get 400 nanoseconds. That's it for this lecture. As always, you know how to contact me if you have questions. We will talk again soon.